So we're going to pick back up with slide 19 in the second set of chapter 3 and 4 slides. All we're really going to do here is introduce acids and bases and the concept of a neutralization reaction, which we'll actually be able to treat a lot like the molecular ionic net ionic equation stuff. So mostly definition stuff here. I think you know a little bit about acids just based on the naming stuff we had to do, but we'll talk more about it all in detail here. So when we talk about acids, there are pretty much two standard definitions that we start with. One is the Arrhenius definition that says acids are substances that increase the concentration of H plus when dissolved in water. So this definition is specific to the behavior of the substance in water, whereas the Bronsted-Lowry definition is the kind of the broader definition where we just say acids are proton donors. So proton equals H plus, right? The hydrogen atom contains one proton and one electron. So if instead of writing H, the atom, we write H plus, then that's just referring to proton, and acids are going to behave as proton donors. So when we talk about the properties of acids, well, we can think about something like vinegar with its sour taste, or when you think about acid, maybe you think about citrus fruits with their citric acid. We also know that acids react with metal, and it essentially converts the metal into a salt and results in the generation of hydrogen gas. We saw this example back in chapter 5 with zinc, but it also would work the same way with magnesium. So in this reaction, we're seeing hydrochloric acid and magnesium react to make magnesium chloride and generate hydrogen gas. We also know that acids react with carbonates and bicarbonates. Bicarbonate, I don't really use that term. We talked about hydrogen carbonates, but the common name is bicarbonate, right? If we're looking at baking soda, the chemical name would be sodium hydrogen carbonate, but a lot of people would just call it sodium bicarbonate. And once again, we see that an acid-base reaction is going to lead to the production of a gas, this time carbon dioxide. So here we see hydrochloric acid and calcium carbonate reacting, and they form calcium chloride along with carbon dioxide and water. So anytime there's a carbonate or a hydrogen carbonate reacting with acid, we'll expect to see some carbon dioxide being generated. We also know that acidic solutions are going to conduct electricity. So they're not all strong electrolytes. In fact, only 7 of the acids would qualify as strong electrolytes, but they all break down partially. Remember, we described them as H plus donors, so they're going to break down partially to release their H plus ion. So there's going to be charged particles present in an acidic solution, enough to make that solution conduct electricity. So there are 7 strong acids, and strong is not relative here, right? This means that they break down completely, they fully dissociate. There isn't a great reason for you to memorize these 7 acids at this point. If you happen to do so, that's fine. But if you're going to take the second semester class where there's a lot more information related to acids, there you might find it useful to memorize these 7 strong acids, but it's not critical right now. So then these are all strong electrolytes, right? They break down completely, so there are lots of charged particles present in our in our solution, so it's going to be a solution that's very good at conducting electricity. So if we're going to talk about acids, then we definitely want to talk about bases as well. And same start here. We've got an Arrhenius definition that's more specific, and a Bronsted-Lowry definition that's a lot broader. So bases, according to Arrhenius, increase the concentration of OH minus when dissolved in water. So OH minus, that's our hydroxide ion, right? So when we're thinking about what's going on here, acids are making H plus, bases are making OH minus. And if you look at that, those are kind of the components of water, right? So in an acid-base reaction, really that's all that's taking place, is the acid is making H plus, the base is making OH minus, and these are going to combine together to form water. So a little bit later we're going to talk about acid-base neutralization reactions, and that's exactly what we're talking about. H plus produced by the acid reacting with OH minus produced by the base effectively is the way we think about what's going on. And then once again here we have a Bronsted-Lowry definition that just says bases are proton acceptors. So that's another picture to think about what's going on, and we can use our example down below to think about it in those terms. H plus is our acid, OH minus is our base. So the OH minus is, in fact, behaving as a proton acceptor as it gets converted into water. So in more complicated acid-base reactions, there'll be more for us to think about, but that's generally what we want to consider. When we think about bases, whereas acids have a sour taste, bases have a bitter taste, so soap is kind of the best thing to think about with regard to that. Bases typically feel slippery, so even if you had a pellet of sodium hydroxide and you put it on your gloved hand, after a while it would start to slide around a little bit. It's kind of what we expect. Again, soap is a good example of a base. If you've ever made soap before, right, basically you take some sort of fat and you add lye to it, which just contains hydroxide ions, and hydroxide is going to break apart those fats and basically make long chain bases, and that's what soaps are. Just like with acidic solutions, aqueous base solutions can conduct electricity as well. They're producing hydroxide ion, but nonetheless, there are some charged particles to consider. When we think about examples of bases for now, anything containing the hydroxide ion is a base. Then another base you might be familiar with is ammonia, NH3. So the N is shown in blue in that 3D model. So just like we have strong acids, there are strong bases as well. And again, not a relative term, right? These things break down completely, so they're also strong electrolytes. So all of the alkali metals, when we pair them with hydroxide, those are going to qualify as strong bases. So we're talking about stuff like lithium hydroxide, sodium hydroxide, potassium hydroxide, etc. Those are all going to be strong bases. All right, NaOH is an example here. Then the next three are the alkali earth metals, right? So calcium with a +2 charge would make CaOH2. Same with strontium, same with barium. So these would all qualify as strong bases. Magnesium hydroxide, magnesium is also an alkali earth metal, but when we make magnesium hydroxide, it just really doesn't dissolve in water, so we can't really gauge whether it would fit into this category of strong bases. So generally we just say the alkali metal and alkali earth metal hydroxides, except for magnesium. So if we go back to our Bronsted-Lowry definition, right, acid is a proton donor, base is a proton acceptor, so we would expect that we could monitor the movement of a proton from acid to base. So in this case, we've got NH3 and we've got water. So NH3 going left to right in this reaction turns into NH4 plus, whereas water turns into OH minus. So going left to right, we'd say water is behaving as an acid because it's giving away an H plus. Ammonia is behaving as a base because it's receiving that H plus in order to form ammonium. So that's the way that we would label things, and essentially, if you want to think about it this way, right, it's this H that shows up here later on in the process. You can also see that things are labeled on the other side of the equation as acid and base. That's for if we're considering the reaction going in the opposite direction, since this one is reversible. So going right to left, then NH4 plus is donating its proton, so it's acting as the acid right to left. And again, going right to left, hydroxide is receiving that H plus, so it's behaving as the base. So in an acid-base reaction, we're really monitoring the movement of the proton, of the H plus ion, and we can see that in order to describe what's going on. Of course, if the process is about observing the transfer of an H plus ion, then that acid needs to have an H plus available to release into solution. A little more acid terminology here. We have monoprotic, diprotic, and triprotic acids, and that's just describing how many H plus ions the molecule is able to release. So starting with our monoprotic acids, we've got hydrochloric acid, nitric acid, and acetic acid. So each one has one hydrogen available to be released. These first two are in the group of 7 strong acids, so that makes them strong electrolytes as well. Acetic acid's kind of been our one and only example of a weak electrolyte. We'll stick with that here. It's a weak acid, and we reinforce that by seeing these reversible arrows to say the breakdown of acetic acid doesn't go 100% to completion, so it creates some charged particles, but that's why we say that it's weak, because it only dissociates partially. Diprotic acids, here's H2SO4, so it shows one H plus released in the first breakdown, another H plus released in the second breakdown. Something to just be aware of. We'll revisit this a little bit later, more in the lab, I would say, in the lab videos, that sulfuric acid, the first dissociation goes 100%. All of the H2SO4 produces H plus and HSO4 minus. But the second deprotonation, where we're releasing this hydrogen, is an equilibrium. It doesn't go all the way to completion. So here we'd say that sulfuric acid is a strong electrolyte, strong acid for the first deprotonation, that's 100%, but the hydrogen sulfate ion doesn't break down all the way, so that would be a weak acid and a weak electrolyte. Triprotic acids, there aren't too many examples of triprotic acids that we typically talk about in general chemistry. Phosphoric acid is kind of the most common one. Phosphoric acid is not one of the strong acids. You can see all 3 of these steps, we describe it as weak acid, which also means weak electrolyte, and that's reinforced by the reversible arrows for all of these. So each time you can see we're losing one hydrogen at a time, going from phosphoric acid to the dihydrogen phosphate ion to the hydrogen phosphate ion. So we should be able to look at some chemical formulas with their equations given and talk about what's going on. So Here it asks us to describe the behavior of HI. Is it an acid, a base, or both? Hydroiodic acid is one of the 7 strong acids. We see its equation written here. So it's producing H+, so clearly it's a Bronsted acid because it's a proton donor. The next one, it's asking about the acetate ion. So the acetate ion, we would say that is what we call the conjugate base of acetic acid, which is written here. So now the equation describing the reaction of acetate, that's showing it receiving an H+ ion. So clearly it's behaving as a base because it's an H+ acceptor. Then the last one it asks about, we just saw this with dihydrogen phosphate, and it asks, is it a base, an acid, or both? Well, it depends, right? We can either see the dihydrogen phosphate giving up its H+ in order to become hydrogen phosphate, or we can see the dihydrogen phosphate receiving an H+ in order to go back to being phosphoric acid. So here it's behaving as both, depending on the reaction conditions. There are plenty of molecules like that. I think dihydrogen phosphate's a very good example. Water is also a really good example because it just depends on the reaction conditions. And we call stuff that behaves as both an acid or a base as amphiprotic or amphoteric. Amphi like amphibian because of kind of both behaviors. So now what we want to think about is kind of really the only chemical reaction we're going to deal with in detail in solution here, and these are neutralization reactions. And so what I mean by in detail is we'll look at some math that goes along with this a little bit later. So we'll focus our look on these reactions to just strong acid reacting with strong base. And you can see we've got hydrochloric acid reacting with, let me do this the other way. I'm going to highlight the individual components. So hydrochloric acid like that, and sodium hydroxide like that. So in this neutralization reaction, effectively, we're going to see what looks like an exchange reaction. So that's why I marked them the way I did, because the HCl is breaking apart and the NaOH is breaking apart. When we think about what water really is, it's a combination of H+ and OH- ions. So effectively, the H for water is coming from hydrochloric acid, and the OH for water is coming from sodium hydroxide. And then meanwhile, the sodium chloride that's forming, that's just the leftovers, essentially. So what we can do here is kind of follow the same protocol as we did for precipitation reactions. Since it's a strong acid and a strong base, we know they're going to dissociate completely. So when we transition to the ionic equation, we can keep that in mind. So then here's my hydrochloric acid broken down. Here's my sodium hydroxide broken down. Here's sodium chloride broken down. But with water, it's just going to stay as is, right? It's written just as liquid water, so I'm not going to show it as broken down into its component parts. So just like the precipitate stayed together, because we have this pure liquid with L here, we'll just write it exactly as is. So you may remember from here, right, after we turn the molecular equation into the ionic equation, we look for the spectator ions and cancel them out to kind of get to the most important part of the reaction. And when we do that, right, you can see the chloride and sodium on each side. Those end up being our spectator ions, so they cancel out, and that effectively just leaves us with the important part of the reaction, which is the H plus reacting with hydroxide. And really, like we said, this is the combination of H plus and OH minus, and so when they react together, they combine and form water. So maybe not in the next video, but the one after it, we'll talk about the math that goes along with neutralization reactions and how we can do some calculations related to it. One other thing to note, I think we mentioned this a little bit earlier, but when we think about these gas-forming reactions, these are still acid-base reactions, right? We're still observing an acid and a base reacting, but we're going to have acid-base reactions that are also gas-forming reactions. And what typically really happens here is we end up forming carbonic acid if we sort of follow through with things pairing up through the reaction. And carbonic acid is going to break down to form water and carbon dioxide. So that's typically what we expect for these sorts of reactions, that the essentially something like this, the H plus and the carbonate ion combine to form carbonic acid, not hydrogen carbonate, right? Hydrogen carbonate's the name of an anion. This is carbonic acid, and that breaks apart into water and carbon dioxide. So there are a lot of acid-base reactions that are also gas-forming reactions. You'll take advantage of the properties of some of these reactions in some of the lab experiments to sort of figure out mass loss, to identify unknown compounds, and just generally to study stoichiometry for some simple reactions. Okay, I think that's all I wanted to cover in this video, just talking about acids and bases. In the next video, we'll talk about oxidation and reduction reactions and assigning oxidation numbers and identifying reduction and oxidation. Okay, so yeah, let me leave it at that, and we'll come back, it looks like, with slide 31 in the next video.